So when we are talking what you are going to talk about, she decided to talk about one of the topics that I think are the hot topics in C++ right now, which is safety. We have heard for some time, oh, C++ is not safe. I would say if C++ is not safe, our civilization is not safe. I'm sorry, because many critical infrastructure in our civilization is on top of C++ software. That doesn't mean that we cannot make C++ safer, because no language is completely safe. And this includes those programming languages that claim that they are safe. I'm sorry, they are also unsafe. So, but we are not here to speak about any other programming language. We are here to speak about C++. And it's true that the committee has been discussing some things that could improve the situation. Some proposals have got in, some proposals are under the way, some proposals were not so lucky, but I am not going to spoil Daniela's talk. I will leave her to tell us the details. So Daniela, thank you very much for coming to Leganés, and the floor is yours. Thank you.
Hola a todos, and welcome to my talk today. First of all, I want to know a little bit more about you. Who of you happens to be at the beginning of the career developing software C++? Please raise your hand. Okay. Who of you is a seasoned developer and has learned a lot about C++? Please raise your hand. Okay. And who of you knows too much about C++? Is disillusioned and has become a member of the committee? Okay. Thank you very much. So, if you remember this particular file name, you will notice that is one of the update files that came with CrowdStrike update last year. And this particular update gave all the 8 million affected systems the ultimate security. It was the purpose of the system that was updated here. This was the CrowdStrike cyber defense system, and the update gave the affected systems the ultimate security because they would no longer boot, and then they could no longer be affected by any cybersecurity threats. This might have been the best marketing stunt ever because it raised awareness of millions of people who were affected by systems no longer booting. But on the other hand, it brought this idea of software security and what can happen in them to the forefront of many people. And not only the people who were waiting at the airports to get a flight, but also to people who have opinions about security of computer languages. And the reason why we had this particular incident is actually what we call software vulnerabilities. And this is what I want to speak about today. It's about security, safety in our code, or possibly even the lack of safety in our code. I want to speak about existing solutions that we have in the language right now, then the upcoming future improvements that we get in C++26. And if time allows, we will also look into the farther future. I'm an electrical engineer, but as most electrical engineers, I pretty much from the very beginning ended up in software development. I'm employed at a small company in Germany. We build custom-made inspection systems like the one you see on the right. I'm the designer of the system, and the entire software in there is written in C++ for the most part by myself. And yeah, that's it. Coming back to software vulnerabilities, there's this paper that is quite famous now. It came out in 2023. It's called The Case of Software Memory Roadmaps, and in there, many of the large software organizations were asked for the reasons they have found what the root causes of software vulnerabilities have been, and roughly 70% of them is memory unsafety. And if you look at the common weakness enumeration website, there's an annual ranking in there, and the latest one is pretty consistently showing the same reasons all over again. It's about out-of-bound reads, writes, and use after freeze. These are the major software vulnerabilities that we are having today. And this scares people. On the other hand, there's a different opinion what one person's memory unsafety or software vulnerability is the other person's chance to also jailbreak into a protected system. So you can have different opinions on software vulnerabilities. Every time I hear people speaking about safety, and they're talking to each other quite avidly, I notice people are discussing with each other, but using the same terms for different things, so they don't really speak to each other. And as you see, we have a long list of things that we can connect to safeties. So what we need is definitions. As engineers, we need definitions, and so we will have a short tour between all the safeties and the meanings of different kinds of safeties to actually have a common ground to speak about. And what I will be using here is this illustration of the C++ object model. To the right, on the bottom, we have the time dimension, the temporal one, where the time goes from the past to the future. On the left, we have the dimension in the memory address space, going from lower address values to higher ones. And on the right, we see a piece of code. We have a struct S, we have a virtual constructor that you also see in the the purple kind of thingy on the top. Then we have a virtual destructor, it's the right purple thing. Then we have 3 member variables in there. These are the yellow ones in here. Then we have, please do not do this ever, but just for illustration purposes, I have a new expression, which means we will allocate and we will call the constructor. Then we have a thread 1, where we define a pointer and later on initialize it. And on thread 2, we have a reference where we can't separate the definition or declaration from the initialization. And all these parts are on the slide, or in the picture. And this is what I will be using in the upcoming slides to show you the different vulnerabilities that we are going to see. One additional thing to note, this dark gray thing on the right and also on the left, this is the underlying memory region. This memory region will be allocated by the new expression before the first constructor will be called. Just to give you an idea what the different colors in here mean. When do we deem a language safe? A language is safe when the language is entirely specified, either in a programmer's manual or in its specification. And here we have 3 different markings in red where we have undefined behavior, where we do not define what will happen. For example, during the construction, we can evaluate variables in our structure that are not yet initialized. The initialization will take place when we turn from gray to yellow. The same is true for pointers. Pointers are objects. They have the same problem. They can be allocated, but they don't need to be initialized at the same time. References are different. They are not objects. So the initialization and giving the first value, the actual thing that we are referencing, this is at the same time. But they both have the same problem at the end. This is what we call pointer sap. When the referenced object is no longer alive, the references to them also become invalid at the same time, even though nothing else in the language is happening. It's just by definition so, which means that when the object is out of its lifetime and we still have the value, for example, in the pointer, and we try to dereference this pointer, this is no longer allowed, but it's still technically possible because our assembly language doesn't forbid this. Spatial safety means that we need to be only accessing the members of a type. These are the yellow regions here. The light gray ones are just padding. They are part of the allocated memory region, but are not part of the object. If we access any of these pieces in memory, this is undefined behavior. In the tabular direction, we also have the safety. For example, in the beginning, as I mentioned, we only have the allocated memory space, and then we call the constructor. And within the constructor, we only need to access member variables after we have initialized them. As long as these boxes are gray, initialization didn't happen there, and this is what we have to really be aware of. In the temporal safety, this also means we have to make sure that we have to obey all the rules that are actually given to us when it comes to what we can do in the constructor, what can we do in the destructor, what can we do within the object in its lifetime. Type safety means that we have to use every type exactly as we have declared this type, and also the sub-objects in there. And this also means, for example, for pointers and references, that we use them only according to the rules of pointers and references, which means we must not use or difference these pointers, for example, to refer to an object that is not yet constructed or is maybe already destructed or doesn't even exist anymore after the allocation of the memory. Bound safety, this is something that applies to all kinds of arrays that we have. The only array that we had in this example is the underlying memory region, the array of bytes. This is why we have these 12 bytes here. And bound safety means that we need to access every array in our language only within the allocated bounds. Lifetime safety is something that I've been alluding to quite early. We need to access any object only within its lifetime. If we don't do that, then we have undefined behavior. For example, this pointer here, before it's given its initial value or after the object has been deallocated, we still have the pointer. It's an object on its own around, and similar kind of thing for the reference, but we no longer must use them to reference a different object that they are referring to. What we also have here is, in particular, the pointer. The pointer, as mentioned, is an object on its own. It has its own lifetime. The object S is a different object. It also has its own lifetime. Now we have a connection between two objects with separate lifetimes, but these lifetimes are entangled, and this kind of entanglement is something that is causing a lot of grief. This is also usually a sign of that we have an incidental data structure here. This is something that we should actually model in a type instead of just using a reference to another object. And lastly, we have thread safety. Thread safety means we need to make sure that we use objects only in a way that we can, for example, call member functions or access member variables in them or the object in its entirety, even in the face of concurrent accesses, and in these cases, the behavior of the object and its invariance and everything in there need to be maintained. It needs to be correct to be used in a concurrent way. Otherwise, if we don't do that, if we violate thread safety, we have the same thing as before. We have references to an object, and we need to employ something like an external coordination. What thread can do something with an object and what the other thread must not do at the same time. So we need internal synchronization, or so this is something that needs to be maintained. This is what thread safety means. Every time I have a picture like this one here on the slides, you may ask questions.
Why?
You also will notice at the bottom right there's a slide number. If you have questions, please keep these numbers in mind that you can get to them. Okay, let me proceed. What do we see here? Or what do you think we see here? What I see is a flight of servers in a data center, possibly containing a lot of valuable information on these server machines. Many people are interested in this information, like the latest cat videos, or maybe important information that unauthorized users want to see. And this means we are speaking about security here. And security is part of organizations or a group of people who are interested in guarantees. We want to make sure that no unauthorized person can get access to any of this information that we have stored in our machines. And this means expected attacks, unexpected attacks, or it may mean unknown attacks. And we have to make sure that we can guarantee that this will never happen. This is what security is all about. Every time I will have a feature in the upcoming slides that is mostly geared towards security, I will use this shield symbol to mark them. On this slide, you see a machine from our company that we have built many years ago. You see a cage, you see a robotic arm moving heavy steel billets from the transport trolleys to the immersion tank and back. You see signal lights, you see security buttons, emergency buttons, whatever. This means we speak about functional safety. In functional safety, we have many different stakeholders in these discussions. We have, for example, the operators. We have the owners of this machine. We have regulators. We have insurers. And all of them have a different opinion what functional safety means to them. For example, the insurers want to make sure that whatever we do with this machine doesn't pose a too large risk to them. Or the operators want to make sure that they don't experience any physical harm, either on their bodies or even also mentally. If the software is so bad and it's crashing so often, this is something that operators really don't like. And this also means the software is not behaving correctly in there. And the same applies to automated systems that want to protect them from accidents to happen or harm to happen. So we need to make sure with functional safety that nothing of this is ever happening to either of the stakeholders with the different points of view to a particular system. There's an interesting quote that I found on the internet, and this says, functional safety is about protecting users from technology, but also protecting technology from users. And I think this is one of the best quotes I found about giving an idea what functional safety really means. And lastly, if we look at this particular picture, most of you would agree this is a car. I would say this is an entity that has aspects of security in it and also has aspects of functional safety in it. Functional safety is marked by this explosion symbol. And if you have seen talks by Bjarne, for example, it was a BMW. I chose to use a competing company from the same region where I live. But what I also see here, this is a moving network of computer systems. It contains a lot of useful and valuable information in it that other people are highly interested in to see, that what we are not interested to ever be seen by other people. And it also can hold a lot of kinetic or potential energy and cause a lot of harm. So in many systems, it's not just security or functional safety, it's both of them. And without the safeties that I've been speaking to before, speaking about security or functional safety is really difficult. With a language that doesn't give us any guarantees, has so much undefined behavior, we will never have security or functional safety. So this is a fundamental kind of thing. Your chance, once again. Okay, let's move on. Let's have a peek at this piece of code. On the left, you see the CPP file. On the right, you see the definition of the types in there. And in line 5 and 6, we see the objects S and U. And now a pop quiz question. How many objects are there in lines 5 and 6? Is it 2? I give you a hint, it's a nice round number. So, is it 2? Okay. Is it 10 or less? Is it more than 10? Okay. I said it's a nice round number. It's 16. Count all the objects and sub-objects in these types on the right, and don't forget the array. There are 8 objects, including the complete one. Okay. The code in here is forming a lot of pointers into the sub-objects of these objects S and U, doing a few operations and checking the results of them, returning the 0 from the function f and calling this function, and this is the entire program. I hope we can all agree this code will compile and it will return 0 when we run it. Anybody who does not agree to that? Okay. What if I change the objects from static duration to putting them into the body of the function? Any changes here? Okay. GCC will complain in line 16 about undefined behavior because now the objects S and U are not yet initialized. And this is undefined behavior if we access them. And this is the first improvement that we get in C++26. This is erroneous behavior. Erroneous behavior is different from undefined behavior in the sense undefined behavior is undefined, as the name implies, but erroneous behavior is completely defined behavior. It's just wrong. And now compilers and the runtime system can say, okay, this needs to be diagnosed and execution may be stopped in here. So this applies both to security and functional safety, because we can get either of them if we have an error in our program. So what should we do? Yeah, we should do what we should always do, initialize our objects. It's a best practice, as you would learn from Klaus. So we initialize it, now we have no more undefined behavior and erroneous behavior. Now I make in the next slide change here. The returned value is no longer assigned to a variable at runtime. Now it's assigned to a compile time constant. I hope all of you know about this const export kind of thing. This designates the RC variable to be a constant. And during the compilation, the compiler is required to assign the value of this constant to RC. And the compiler does it by invoking the function f. So we all know what the result would be. It would be 0, but does it change the behavior? Any opinion? Okay. Now the compiler will complain. In line 16, we have undefined behavior because of an out-of-bounds access. You notice In line 11, we could form a pointer past the end of an array. This is totally valid. But we must never dereference it. So this is the reason why all compilers will stop further compiling this or saying this is not a valid constant. Any more? Okay. We have the same, of course, in line 25, but even more so, we have another different complaint by all compilers, and it says we must never access a member of a union that is not the active member yet. We were initializing the union in line 7, but the initialization of a union is not all of the sub-members, sub-objects in a union. There's only one at the same time. And we were initializing the member A in the union, but we have been forming pointers to sub-objects B and C, and these objects just don't exist yet at compile time. So we must never dereference the pointers to them. And this is why the compilers are complaining. And this gives you a glimpse of the power of constant evaluation and const expr in general. We have seen a couple of undefined behaviors yet. And if we look at the current document, I've counted around 140 mentions of undefined behavior in them. There might be a few less these days. We have squashed some of them in between, and some of them might be duplicates, but there are way too many. This is why neither C nor C++ is ever considered to be a safe language. But, of course, a large group of people say this is actually fine. And we have been using this language for such a long time. Why should this be a problem at all? In fact, we use undefined behavior to get all of the performance out of the language without specifying every corner case in different behaviors, like, for example, what happens at the end of the representable region of an integer. Is it saturating? Is it wrapping back? Is it doing something else? We don't know. We say the compiler does whatever it does in the most performant way. But on the other hand, this means we cannot define the behavior of what happens in this particular case. And we have many, many situations like that. So this is fine in this point of view. But on the other hand, this is also not okay, because if we want to program in a correct and safe way, we have the program defense guards, unless we forget them, but usually we have pieces in our code that we want to use to make sure that we deal with these corner cases. Modern compilers are now so capable in figuring out what is happening in our code that optimizers might not only use undefined behavior to squeeze more performance out of our code. They might even remove all our defense guards or even larger parts of our code. And this is something that is really baffling a lot of users. And it's difficult to actually handle this kind of thing. The influence that undefined behavior can have onto our code is so huge. The blast radius of modifying the behavior that we expect from our code is pretty much unlimited. And this is why this is in many cases not fine. And those of you who have seen different kinds of behaviors with different compiler switches, this is one of the results we can get if we are having undefined behavior in our code and we don't recognize it, and we have so many chances of it. And as we've seen before, we can fight or figure out where we have undefined behavior by using constant evaluation. Because by the language, constant evaluation is mandated to refuse and diagnose all occurrences of undefined behavior. But, this is the big caveat, only during program execution. The execution is happening within the compiler, but only then undefined behavior will be diagnosed by constant evaluation. So this means if we use these rules of constant evaluation, we can use it to improve both security and functional safety at the same time. And what does it mean when we go back to this illustration from the beginning? The light gray and the dark gray parts are gone. The compiler makes sure that we don't do anything with, for example, the padding bytes. We don't have an allocation in there. It makes no sense within the compiler to have a memory allocation. The compiler makes sure that we use the pointers and references only exactly as they are specified to do in a well-defined manner, and even more. So you can use this to make sure that all the corner cases are no longer in your program. Let's look at this particular piece of code here. It looks pretty simple. It's a function f. It points to an array. Actually, it points to the first sub-element in it. And it has two Boolean parameters. It has a simple algorithm in there. This is just for illustration purposes. Usually in your code, it might be hidden in much larger parts of your code in there, and then it will dereference this given array. The array is defined as a constant. As mentioned, we can use constant evaluation, like here in the static assert, to make sure that we don't have undefined behavior in our code, and we can use it at runtime. So far, so good. The program does exactly what it is supposed to do. It meets the requirements. The compiler is happy. The code coverage checker is happy. Our program manager is happy. Ship it. Until we have another combination of things that we can use to give to our function. And we test it, and now it fails. Because this testing that we have done before with the 100% code coverage is not enough. We need 100% path coverage, and not only all the execution paths through our code, we also need to make sure that the same kind of things applies to our variables in there, because we can have overflows in variables. And these kind of things are also only covered if we actually assume these particular values in there. So due diligence in our testing is paramount, as it has ever been. Summarizing constant expressions, starting from the humble beginnings in C++ 11, it has improved very much over time. And in C++26, it will improve even more, so we can do way more tests at compile time in our code, and we should actually use all of that. Let's get back to the same function once again, now a little bit simplified. What we've seen before is that we actually have an implicit contract in this code. Dereferencing the pointer to the array means we need to make sure that the index lies within the bounds of the array, as I've already been alluding to in the bound safety kinds of slide. But unfortunately, there is no information about the size of the array here. We could formulate it like this, using the reference notation and giving the actual size of the array that we are giving to the function. But honestly, giving a fixed size of an array to a function, I don't like that. It's not generic. We could make it generic by making it a template, but yeah, templates for this simple function? Template load? No, not really. Okay, let's give the actual size of the array as an additional parameter at runtime. Now I have to change the call side too, and who makes sure that the array size and the parameter that we have been giving to the function actually relate to each other. Yet another opportunity to fail here. Okay, and this is what we should really do. We should use our standard library, using the span in this particular case, where we combine the underlying array and the size of the things that we want to index. We use strong types instead of just pure booleans. Yet another point where we can fail, for example, by switching the order on the call side. And please don't call your functions f, give them proper names. And this is what I call contemporary C++. Maybe you've seen the talk 3 years ago that I gave on this particular topic, where I coined this particular notion of contemporary C++. This means use all the power of C++ that we have today and use it wisely. But still, we need to obey to the contract. In all these slides, I was mentioning, please do a range check here. Just putting it into a comment isn't enough. The compiler doesn't read comments. And this is an opportunity to fail in our code just as well. And luckily, with C++26, we no longer need to do that if we use classes from the standard library, because a hardened version of the standard library will do the checking within the library itself. So we no longer run afoul of failing to do our range checks in our own code. This is proposal 3471. It was a remarkable proposal. It was pretty much unanimous consent to put it into C++26. This is the best thing that you can get with a proposal. And we can probably get a hardened standard library today. You can use it if your compiling environment allows. If you want to learn more about the hardened standard library, watch this particular talk here by Louis Dion. He is a member of the Apple libc++ team, and this team was pushing this proposal forward and bringing an implementation and assessing the performance impacts that a hardening of the standard library will bring. And this was the reason why we decided it's actually totally worthwhile to have a hardened standard library in C++26. Because if you look in the standard document, you will see in the library section of the standard, we have preconditions in there. And a large part of these preconditions are checked in the hardened version of the standard library. And this checking does not only take place in certain modes of compilation, like we had, for example, with the Microsoft standard library in the debug version. This was hardened for 20 years or so, but it was never hardened in the release build of a library. Now, the hardened standard library is required to give us the same guarantees in all compilation modes. This may mean we can still ignore it and get back our beloved undefined behavior, or we do actually try to detect all contract violations that we have. I mentioned a different proposal. If it's not yet implemented, a hardened standard library has to stop execution immediately. This is for the security people. And with this other proposal, it means we have to detour into a contract violation handler, and the contract violation handler will determine what should be done if we have a contract violation. This is mostly for the functional safety improvement, but also for correctness, of course. Implementations are even allowed to go beyond what's been proposed. And one of the things that I really like is one of the additions that we have, for example, in the Microsoft standard library is what's called destructor pointer tombstones. If you place tombstones at destruction time into our types, we can even resist use after free, because now we have marked our pointers to no longer point to objects that have been there before but are no longer there. And now we get a contract violation also because of the invalid pointer value. And these additions on top of the proposal are available, as I mentioned, in the Microsoft standard library in libc++, and I think libc.c++ just as well, but I'm not too sure about that. Last week, I checked if this is actually true, and I compiled this piece of code here. It's very simple, it's just a vector that I've initialized with 3 values, 1, 2, and 3, and blatantly ignored the contract that the vector has by indexing, giving invalid indices 3 and -1. And the non-hardened version is working just as it has ever been in the past 20 years. This is what you can expect from undefined behavior. It works, but the results are undefined. And the program is telling me everything is fine, nothing to see here. With hardening in place, at execution of this program, it will be stopped entering line 7 in this example, and the return value will be a status code that says we have a contract violation in our code. And this is just in release mode. So this works exactly as advertised. And I think this is one of the greatest things we can expect from C++26. Any more questions? Okay. I've already been alluding to proposal P2900, contracts for C++. Long-term visitors of this conference might think, contracts? Wasn't this a thing many years ago when Bjarne and you were here and so happy about having contracts in C++? Yeah, disillusioned members of the committee. But we should get it in C++26. And all people who already know what pre-contracts are, these are similar to what we have in Eiffel, for example, and Ada or D. We have seen it in the standard hardening of the standard library. Contracts are not for the language or the library implementers. Contracts are for you. Contracts are for the developers, that we can check our own programs and defend against errors. It helps you to perform design by contract, and you can use it in particular to check the correctness in your programs. Today, you might have code like this one here, with a function with a precondition and a postcondition that is just written down as a comment in human language. And we might have a C assert to make sure that our expectations are met. But if we call our code, the compiler doesn't read comments, and in release mode, asserts are not a thing. So this is just commenting our code, not really checking our contracts. With the contracts proposal, this is the same function again, but now we can annotate the interface of our function with a precondition, and the Boolean expression in there will be checked at runtime. The same is true for the postcondition in here. I don't go into details, read the proposal if you are interested or watch a talk about this. And also, the function parameters are implicitly constant. So you can't use this contract feature to fix up errors in your functions. You can only check them. And this is a good thing. The assert that we have seen before is now a contract assert. It behaves similar to the pre- and post-conditions in the interface of the function, and it applies to all compilation modes just as well. And on top of that, we have another new feature in C++26. This is called observable checkpoints. And these checkpoints are used to make sure that the compiler doesn't remove our contract assertions, it doesn't remove our defenses against unwanted behavior. It actually means that we build barriers within our code where compilers and optimizers must not look beyond and use this information from later on or from earlier to change the meaning in our code. So the blast radius of modifications, unwanted or even unnoticed modifications in our code is quite contained right now if we ever use observable checkpoints. And contract asserts are implicitly giving us observable checkpoints. This means that whenever we call a function out of contract, it will not move along unnoticed. We now go into a contract violation handler, and within these contract violation handlers, we have a chance to deal with this out of contract call. Because in this object that we get, along with the detour into the contract violation handler, we also get different contract evaluation semantics. You've already seen the ignore semantics, which, as the name implies, does nothing. And we have already seen this quick enforce semantic in the standard library hardening, where we immediately stop the program. But we also have the observe semantic and the enforce semantic, where whenever we get into the contract violation handler, we can, for example, log it and get a list of things that we have to put our attention to and make sure to improve the correctness in our programs. And we also can save in the enforce semantic, do not do on just the logging, but also terminate the program. Termination means now you probably have entered a safe mode or possibly even a secure mode. This also happens at compile time. The compiler will make sure not only undefined behavior is checked, but also contract violations are checked and tell you, okay, this is not within contract. This is in particular made for the security people. After all this, can we get to safe C++? And this is the core safety profiles. Unfortunately, this is not in C++, Sec 26. But to give you a glimpse of an idea, in the 70s we had C, and we pretty much embraced it and incorporated for the most part into C++, but C has a lot of undefined behavior in it. There's this paper in the C committee from 2 or 3 years ago. They have been enumerating all versions and all occurrences of undefined behavior, and there are hundreds of them just in the core language and more than twice as many in the entire language, and this is tainting C++. Even our extensions, even C++ 26, and C++ adds to undefined behavior just on its own as well. Now we have erroneous behavior and the hardened library. Now we have safe parts in the language. And with additional abstractions, this is what I would deem contemporary C++, but we still have all this undefined behavior in here. And profile annotations give us a means to make sure that we can ask the compiler to not use unsafe language constructs that we have inherited from C, or we can instruct the compiler to incorporate range checks, for example, when indexing pointers. Pointers are not objects, so we have a language level mechanism to figure out when we are out of contract. But in the end, there are still parts that have been left. This is what I call untractable, undefined behavior. This is not possible to stop with the profile annotations. But unfortunately, this is not yet part of C++ 26. It will hopefully be part of C++ 29, or I don't want to promise too much. I see I'm running out of time. Okay, let's have a glimpse at going beyond C++26. What we couldn't tackle so far is a comprehensive way of tackling lifetime safety. Maybe we should discuss a proposal that we have in the standard that's called Safe C++. There's actually an implementation of it in the Circle compiler. But as it turns out, this pretty much needs a full, separate, additional implementation of the standard library. This means a lot of efforts to all implementers, not only in the library, but also in the compiler. This is a quite recent proposal, and this is why it's not discussed in the committee yet. Then this is what I prefer. I would say we should embrace much more value semantics and whole-part relationships. You might notice I've mentioned these incidental data structures. We should no longer make them incidental data structures, but real data structures. References and pointers should just live under the hood, and the compiler should decide when it's worth using pointer and reference semantics to improve performance. And we get exclusivity for free. So we also get thread safety implicitly by that. Currently, there's a third way proposed. No, not yet proposed, but it's explored. I'm looking forward to see it. Maybe we can tackle thread safety, as I said, something like value semantics, whole value, and part relationships would give us that, such that they can actually guarantee exclusivity, which means that we shift objects, whole objects across thread boundaries and don't allow references crossing thread boundaries. This might require data flow analysis, but if we would pursue non-trivial relocation, something that I've not been talking about, this will require data flow analysis, but we have the same kind of thing if we would go into the direction that Rust is going to. This is data flow analysis and lifetime analysis. And possibly we can even tackle all undefined behavior in C++. And this is something that will be pursued in a white paper right this evening. There is the first talking within the evaluation working group in the standard library, in the standards committee, where we will think about what we can do with erroneous behavior, contract profiles, and even beyond that. So we will decide the scope of the thing that we want to tackle within this white paper. The white paper has the benefit that it's much quicker than every international standard and going through all the levels that Daniela has been showing us in the introduction. So this might be even quicker than the advent of C++26, but I'm not sure. I don't want to overpromise anything here. So, in summary, we have been speaking about why it's so important, what the difference between security and functional safety is, why all the safeties are so important, the importance of compile time testing. Hardening the standard library gives us many, many benefits. C++ contracts will help you in your daily work. C++ profiles will give us a brighter future. And let's see what's beyond that. And please never forget, this is the fundamental truth in software development. Etzke is totally right. Simplicity is the prerequisite for reliability, and please don't mistake simplicity with familiarity. Here you find some of the things that I've been speaking about in the slides before. I will be putting the PDF of these slides. Do you have a point where to put it? I will put it there, and I will also put it on my GitHub. And with that, I'm done, and thank you for your attention, and have a nice break.
So thank you very much, Daniela. We have some time for questions. Yeah, I knew you had a question. You are in the queue.
Hi. First of all, thanks. I really like the visualization part of the pointers. I think it's really explanatory. And I will like you to return to 25.6, if it's possible, please. Just a moment.
Excuse me, I'm old, I need glasses. There are no
20
numbers in here.
25.6. Yeah, that one. Yeah. My question is about the post part in the beginning. Why do we need the R two dots R different from X? Why not use just R different from X over there? I'm not sure. Maybe it's about the syntaxis or the construction. I'm not sure why we need to put the R 2 times over there.
Ask your professor.
You're not quite well. Well, it's just that you need to introduce a name for the return value of the function. So we need some way of saying it. We don't need to say the type, because of course the type is the return type of the function.
The return is just an PR value, and it's not named. So we need a name to refer to it.
Thank you.
Hi, I have a question about hardened standard library. Is it doing the same as sanitizers do? And if so, why do we need this in the first place?
So sanitizers are really helpful. You should always use sanitizers if you possibly can. But the hardened standard library just makes sure that even if you ship your code to the customer, usually you don't ship it with the sanitizers enabled. With the hard standard library, now you have a lot of checks. Also, then your code is shipped to the customer. And the performance impact is made such that it's so low that you can really afford shipping the hardened standard library to the customer. Does it answer your question?
Yeah. So it basically meant for production, not for testing.
No, it's not for testing. It's just for protection. You can use it for testing as well, but like you can use everything that you can imagine for testing, and every bright idea is a good idea.
And in some environments, you don't want to ship into production something with sanitizer enabled. There are risks in doing that thing.
The sanitizer itself can be a target of a security vulnerability itself. Just like I've shown in the first slide with the update, the cybersecurity defense system was the actual problem in there. Yeah, the attacker was sitting already on the machine. It was just triggered by the update.
By the way, for those of you that want to know more of the current context proposal, Ran over there will be giving a talk on Friday. So you will get more details there, which doesn't mean that I love those details. Any other question?
Here's one
Oh.
on the right.
Well, thanks for the talk. You mentioned there's like a third option for safety, right? Now, I know one proposal that embeds the safety to qualification, like const, but the keyword is safe, I think. Is it considered at all in the committee?
I don't think so.
Okay. So I think the proposal says like there's like a safe keyword similar to const, making the function like safe, and therefore making the safety type of the function or type.
No.
I'm not aware of that, but I think a typical mistake in some other languages is considering that safety is a binary property, yes or not. While I think in the first part of Daniela's talk, she made very clear that Daniela has multiple dimensions that are orthogonal one with each other. So you cannot say, disable all my safety. Probably you only want to disable pointer arithmetic, or you want to disable only integer arithmetic, or any other property of safety. But yeah, just that doesn't mean that you don't want to leave working the rest of your safety nets. More questions?
Thank you. Thank you for your talk. I mean, including all these features, all these safety features, of course, has a cost. I mean, has there been an analysis of performance impact of these new safety?
Analysis of the performance impacts, and the performance impacts measured by, for example, the Apple library team is so low that nobody in the committee was concerned about it. And this was the reason why we are totally happy to vote it into the standard.
There are at least two different studies, one coming from Apple and another one coming from Google.
Yes.
And the average performance loss that you have is 0.3%. So wouldn't you pay 0.3% for being in a safer environment? I was remembering during the talk, I think it was Donald Knuth who said, oh, if the result doesn't need to be correct, I can make it arbitrarily fast.
Right. In fact, the power of optimizers nowadays is so great not to only exploit undefined behavior in ways that we never imagined before, it also gives us the power to reduce the performance impact to such low levels if we make it correct.
Last question. They look like they want coffee. Thank you very much, Daniela.